Good day, Math 31s. So today we're talking about exponents and logarithms, specifically logarithms. So we finished the unit about exponents, and now we investigate, one, what a logarithm is and how to interpret it. So the point of today is to, like exponents, look at the characteristics of logarithms. So really we don't know what a logarithm is, only that maybe we've seen it in chemistry, acids and bases, or maybe we've heard about it before. So in exploring a logarithmic graph, to understand it, we first need to start again with exponential functions. So what we're going to do is draw 10 to the power of x, and I've done that for us in your notes. We're also going to then draw 2 to the power of x and label it. So 10 to the power of x is saying 10 to the negative 1. 10 to the negative 1 is flipping it over and saying 1 divided by 10 to the positive 1. 10 to the 0 is 1. 10 to the 1 is 10. 10 squared is 100, 1,000, and it might be a bit tricky to actually fit anything on this graph because 10 is such a strong base. 2 is a little bit more convenient because we can say 2 to the negative 1 is 1/2. 2 to the 0 is 1. 2 to the 1, 2 squared, 2 cubed. And a few of these might fit more nicely on here. So what we're doing is we're taking our f of x equals 10 to the x and comparing this to a g of x, which is 2 to the x, which we can sketch by using our plug in a negative 1, a 1/2 comes out. Plug in a 0 and a 1 comes out, and there's a meeting point. Plug in a 1, 2 comes out. Plug in 2, 4 comes out. Plug in a 3, 8 comes out. Technically, you could plug in a 4 and a 16 would come out. Ultimately, we have an exponential function that levels off to our horizontal asymptote, which we can call g of x is equal to 2 to the power of x. So we can see that the 10 to the x is more steep and growing faster than the 2 to the x one. What we're going to do is draw the inverse of f of x and label it as a log function. Now this is what a logarithm actually is, an inverse. So we remind ourselves in our first chapter that an inverse was a diagonal reflection along the line y equals x. That was an intent statement. So reminding ourselves that we're reflecting along the line y equals x. Now it's pretty challenging to think about reflecting diagonally, so the way that we can interpret this more easily is to think of the switching as x and y. So let's draw 2 to the x as an inverse to start. So instead of negative 1, 1/2, 0, 1, 1, 2, 2, 4, 3, 8, we're going to flip the x and the y around and say input 1/2, output negative 1. Input 1/2, output negative 1. Input 0, or input 1, outcome 0. Input 2, outcomes 1. Input 4, outcomes 2, and this one's actually incorrect. Input an 8, outcomes a 3. Technically keep going. Input a 16, outcomes a 4. The next one you think about after the 3, 2 to the 3 is 8, 2 to the 4 is 16, 2 to the 5 is 32, and so if you were to go all the way and plug in 32, 5 comes out. We can't quite fit that on the graph. So what we've got is this reflection, this inverse of the exponential function, that instead of leveling off on the x-axis, is going to actually level off on the y-axis and become our vertical asymptote. So this is our first logarithmic function probably ever drawn. It's a base 2, and we write it as a subscript right after log. So this is y equals log base 2 of x. X is your input, y is your output, and just like trig, the x is tied to your log. Kind of like sine of an angle, this is log of an x value. So they're tied together. So if we were to do the inverse of 10 to the x, again, we've only got a couple of points to select from, but if we put in a 1 over 10 input, a negative 1 comes out. Negative 1 over 10 is very hard to draw, but a negative 1 comes out. It crosses over at 1, 0. And the only one we might be able to fit on here is 10 goes in, 1 comes out. And so this is still going to level off, and it'll be very, very sharp in how it looks. So you can see that the logarithmic one is leveling off, but maybe not as fast as log base 10. And so you can see that there's this faster and faster increase for 10 to the x, and a slower and slower and slower increase for log base 10. 2 to the x, log base 2 of x. And those are reflections of each other. So it is important to know that an exponential function and a logarithmic function are inverses, and you can again see that diagonal reflection. So if you're ever asked to sketch a logarithmic function, it's probably easiest to think about it as an exponent first. We'll pick on something kind of simple, just like we did y equals log base 2 of x. To graph log base 2 of x, you might actually think about its inverse, y equals 2 to the x. Pick some points on your 2 to the x, and then flip them. So you've got a 1/4, a 1/2, a 1, a 2, a 4, an 8, and maybe you flip all those around so that on your graph of log base 2 of x, you can graph a 1/4, negative 2, a 1/2, a negative 1, a 1, 0, 2, 1, 4, 2, 8, 3, and it really is challenging to think about this exponential function backwards, inverted, without actually writing something down. So you're thinking about a 1/4, negative 2, a 1/2, negative 1, 0, a 1, 0, 2 to the right, 1 up, 4 to the right, 2 up, and now it's a little bit easier. You can think about 2 to the 3 is an 8, 8, 3, 2 to the 4 is a 16, and once you have enough of a pattern, we can fill in our smooth curve connecting those. And this is maybe our first, again, solely logarithmic graph. Now the difference here between an exponent and a log is that for exponential functions, as x increases a little, x might change by one value from here to here, y is changing faster and faster and faster. Y is changing really, really fast. For a logarithmic function, which is a reflection, as x increases a lot, y increases a little. And you can visualize this a little bit more above. Imagine I look at the next few locations. 16, 4, 32, 5, 64, 6. Now we're way off the page here. 128, 7. We would have to be at 1024 to the right to only go 10 up. And that's very, very extreme. As x is going up a lot, we're only traveling slightly up. We're always increasing, but it's just slower and slower. So this is what a logarithmic graph essentially looks like, but being able to use exponents is very, very helpful. And that's actually what we do even for working with it as an equation. So we can convert a log to an exponent and retain its relationship to help us interpret it, because logs are very, very tricky to interpret. So for something like 10 squared is 100, we could turn this into a logarithmic expression by using kind of a loop. If you repeat that, 10 to the 2 is 100, 10 to the 2 equals 100, we can write this as a base 2, or a base 10, and say 10 to the 2 equals 100. And if you do this loop where you move over to the other side, 10 to the 2 is 100, we can better interpret logs. So it's this idea that with a base, maybe b, some input of m, and some output y, can be thought of as a little bit of a loop. B to the a equals m. Now those letters aren't specific to any formula, but it's that loop that works. So let's try to interpret a few questions below and see if we can convert them to its inverse form. So log base 2 of 8. If you're asked to evaluate log base 2 of 8, the hope is that you could come up with the answer of 3. How do we do that? Well, we're thinking about this loop to say base 2, 2 to the power of 3 is 8. Keep saying that relationship. 10 to the 2 equals 100. And follow in those positions. 2 to the 3 is 8. Do the loop. 2 to the 3 is 8. And these are equivalent values, but thinking about it in its inverse form. 3 to the 3 is 27, which is true. In logarithmic form, the base is 3, and we would have to say 3 to the 3 is 27. So if you were to evaluate log base 3 of 27, plug 27 into the equation, what comes out? A y value of 3. Hard to visualize that graphically just now, but the loop helps take care of some of that work for us. So a couple to try. If you wanted to pause the video and try them and then check after, now is a great time. Otherwise, I'll keep going. So b is 10 cubed. So we're saying 10 to the 3 is b, base 10 to the 3 is b. So we get a little bit more variable to deal with more conceptual questions. 3 to the m is 50. 2 to the 4 is 16. 2 to the 4 is 16, which is true. 4 cubed is 64. And if we know that loop, it allows us to interpret logarithmic expressions a little bit more conveniently, which we're going to do next. So often you're asked in math to evaluate. Evaluating is another way of saying, all right, number crunch and tell me what comes out. We're being asked to evaluate logarithmic expressions. One of the challenging things about the log function in a calculator is that when you type the log button, it only allows us to use base 10, and this is base 7. So if you go into your calculator and you type the log button, which is on the left, in the bottom there, it'll actually only be base 10. So how do we evaluate the answer to this? The answer is going to be whatever x is. We're going to do this using the loop. So if we do that loop thing, we can say 7 to the x is 49. And all of a sudden, even though we're evaluating a logarithmic function, we're now evaluating an exponential function, which we've seen before. 7 to the x is 7 squared. Match up those powers to say x should be a 2. And there's your answer. So log base 7 of 49 is 2. Similarly, 6 to the what? 6 to the what is 1? Well, 6 to the 1 is 6. No, you'd have to maybe write this as 6 to the x, 6 to the 0. Anything to the 0 is 1. X would have to be 0. And you could visualize this. If you plug 1 into a logarithmic function, what comes out? Even though this is a base 2, a logarithmic function will always go through an x-intercept of 1 unless there's some sort of transformation. Plug in a 1, out comes a y value of 0. They get a little bit more complex, but similar idea. 2 to the x is the square root of 8. 2 to the x is 2 cubed to the power of 1/2. That's what a radical is, a power of 1/2. So let's say this 2 cubed is to the power of 1/2, or 3/2. Matching up those powers, x is 3/2. So this is going back to our lesson in exponents and doing an exponential question within a logarithmic question. Now, if ever you don't see a base written, it's an assumed 10. So if you don't see a number written there and it says log of input, we know that it's an assumed 10. It's actually one of the most common bases to use, and that's what you use in chemistry. So if this says base 10 to the power of x is 1/10, 1/10, we can rewrite this as 10 to the x equals 10 to the negative 1, and x would be our negative 1. So the trick is to think in exponents, and it will make your life a little bit easier for evaluating logarithms. So I did ask for you to try a couple, and again, a good chance to pause the video and see if you can attempt some of these, ultimately asking, what is x? So 5 to the power of negative 3 is x, doing the loop, and evaluating 5 to the negative 3 is the 1 divided by 5 cubed, which is 125 as a denominator. Right, so we've got an x that has to be squared, should give us a 36. X squared is 36. When we square root both sides, we get a positive or negative 6. But it's important to know that dealing with logarithms or exponents, bases can never be negative. So even though mathematically we're getting the square root of x and square root of 36 is a positive or negative, we only have a base of 6 that's possible. So that's a bit of a tricky one. 64 to the 2/3 is x. And again, we're starting to do that loop a little bit faster. How do we solve when there's a fractional power? Well, without a calculator, we can still remind ourselves that that 3 denominator is asking for a cube root of 64, and we can deal with that squared after. So I broke that 2/3 up into a cube root and a squared, and the cube root of 64 is 4, which we can then square afterwards, which gives us a 16 as our final answer. One last one, we've got a 9 to the power of x, gives us an 81 with a 5th root. And so we can get this 81 to be a 9 squared. And that 9 squared still has the 1/5 power. So power of a power makes a 9 to the 2/5, 9 to the x. And those x's, or those powers should match. X should be 2/5. And a bit of a weirdly styled one, some conceptual depth that we're looking for. One question says log base a of b is c, just a statement, and log base b of a is what? Question is solve for x. These questions aren't always obvious in how to deal with them, but you might try to turn them into a exponential form to be able to interpret. So if we do that for both of these, we've got a to the c is b, and we've got a b to the x is a. Now, if we could figure out what x is, we would have the answer to our question. If we could get x. So somehow we can put these two things together. We've got a little bit of information on the left that maybe we can put into this example on the right. Well, if it tells us what b is, shouldn't we be able to replace the value of b, a to the c, into the one on the right? Well, if we try that, we could rewrite b by saying a to the c to the x. So b is a to the c to the x is a. We actually have an exponential question just like above. A to the cx is equal to a to the 1. And if we take those powers and we equate them, we can say cx should be 1. What is x? 1 divided by c. A very conceptual question and a tricky one nonetheless, but sometimes we can use a bit of information provided and help answer something a bit complex. As we kind of continue on to our last little bit of examples, we're talking about earthquakes. Earthquakes are based on a Richter scale, which tells us how shaky the ground moved. So The Richter scale is a logarithm with base 10. This means a value of 4 is not twice the magnitude of a value of 2. So when you hear in the news that there was a Richter scale, there's an earthquake with a magnitude of 4 versus a magnitude of 2, it's not like they're twice as intense. The Richter scale makes it a bit more complex. So imagine for a moment you had a needle that was measuring the shakiness of the earth, and it measured some intensity. So this intensity could be measured thinking like a sinusoidal function as a bit of an amplitude. So what happens is this intensity, this sort of amplitude or max to min range value, gets plugged into a logarithmic equation. Amplitude of vibrations goes as your input, and the Richter scale comes out. So log of the intensity is the Richter scale value. You could also be asking, if you know the magnitude, if you know the Richter scale value, you could get back to the intensity with this formula, where I0 is an initial value that's very, very close to 1. So let's compare vibrations that were 100 units. So 100 units is the shakiness. The Richter scale value is log of that intensity. And if you type that into your calculator this time, press the log button, 100 is your input. What comes out is 2. Your Richter scale value is 2. So this was a magnitude of 2.0 in the news. If the vibrations were 10 times as great, 1,000 units, the Richter scale value would read log of 1,000, 10 to the 3 is 1,000, or type it into your calculator, log 1,000, a 3.0 comes out. So if there was an earthquake that went from a 2 to a 3, it's actually 10 times as intense. 10 times to going from a 2 to a 3. You might then ask, well, what would happen if it was a 2 to a 4, or a 2 to a 5, 2 to a 6? Well, let's compare a realistic scenario. The very recent earthquakes in Chile and Haiti had values of 9.5, one of the highest ever, and a magnitude of 7.0. With these in mind, how many times larger is a Chilean earthquake than the Haiti earthquake? So if we're comparing how much more intense they are, we're not just going to divide 9.5 by 7.0, because the actual intensity is based on their original I value, or their original vibrations. So what we're going to do is consider this Richter scale value, which I'll call magnitude, which is based on log base 10 of our intensity. And if we